Welcome to Tesla AI Day 2022. I do want to set some expectations with respect to our Optimus robot. As you know, last year it was just a person in a robot suit. But we've come a long way, and it's I think compared to that, it's going to be very impressive. So should we bring out the bot?
Before we do that, we have one little bonus tip for the day. This is actually the first time we try this robot without any backup support, cranes, mechanical mechanisms, no cables, nothing.
Yeah. I want to do it with you guys tonight, but it's the first time, so let's see.
You ready? Let's go.
Go.
I think the bot got some moves too. So this is essentially the same full self-driving computer that runs in your Tesla cars, by the way.
This is literally the first time the robot has operated without a tether. Was on stage tonight. So the robot can actually do a lot more than we just showed you. We just didn't want it to fall on its face. So we'll show you some videos now of the robot doing a bunch of other things.
Yeah, we wanted to show a little bit more what we've done over the past few months with the bot, and just walking around and dancing on stage. Just humble beginnings, but you can see the autopilot neural networks running as is, just retrained for the bot directly on that new platform. That's my watering can.
Yeah, when you see a rendered view, that's the robot. That's the world the robot sees. So it's very clearly identifying objects. Like this is the object it should picking it up.
We use the same process as we did for autopilot to collect data and train neural networks that we then deploy on the robot. That's an example that illustrates the upper body a little bit more.
What you saw was what we call Bumble C. That's our sort of rough development robot using semi-off-the-shelf actuators. But we actually have gone a step further than that already. The team's done an incredible job. And we actually have an Optimus Bot with fully Tesla-designed and built actuators, battery pack, control system, everything. It wasn't quite ready to walk, but I think it will walk in a few weeks. But we wanted to show you the robot, something that's actually fairly close to what will go into production, and show you all the things it can do. So let's bring it out.
Do it.
With the degrees of freedom that we expect to have in Optimus Production Unit 1, which is the ability to move all the fingers independently, to have the thumb have 2 degrees of freedom, so it has opposable thumbs, and both left and right hand, so it's able to operate tools and do useful things. Our goal is to make a useful humanoid robot as quickly as possible. The Optimus is designed to be an extremely capable robot, but made in very high volume, probably ultimately millions of units, and it is expected to cost much less than a car.
I'll just bring it
So,
directly to the right here.
I would say probably less than $20,000. The potential for Optimus is, I think, appreciated by very few people.
Hey!
As usual, Tesla demos are coming in hot.
So that robot that came out and did the little routine for you guys, we had that within 6 months. Built, working on software integration, hardware upgrades over the months since then. But in parallel, we've also been designing the next generation, this one over here. Obviously, there's a lot that's changed since last year, but there's a few things that are still the same, you'll notice. We still have this really detailed focus on the true human form. So on the screen here, you'll see in orange our actuators, which we'll get to in a little bit, and in blue, our electrical system. So in the middle of our torso, actually it is the torso, we have our battery pack. This is sized at 2.3 kilowatt hours, which is perfect for about a full day's worth of work. What's really unique about this battery pack is it has all of the battery electronics integrated into a single PCB within the pack. So going on to sort of our brain, it's not in the head, but it's pretty close. Also in our torso, we have our central computer. So we still are it's gonna do everything that a human brain does. Processing vision data, making split-second decisions based on multiple sensory inputs, and also communications. So to support communications, it's equipped with wireless connectivity as well as audio support. And then it also has hardware-level security features, which are important to protect both the robot and the people around the robot. So now that we have our sort of core, we're going to need some limbs on this guy. And we'd love to show you a little bit about our actuators and our fully functional hands as well.
So there are many similarities between a car and a robot when it comes to powertrain design. The most important thing that matters here is energy, mass, and cost. In the particular case, you see a car with 2 drive units. And the drive units are used in order to accelerate the car 0 to 60 miles per hour time or drive a city drive cycle. While the robot that has 28 actuators, it's not obvious what are the tasks at actuator level. So we have tasks that are higher level, like walking or climbing stairs or carrying a heavy object, which need to be translated into joint specs. The rotary actuator in particular has a mechanical clutch integrated on the high-speed side, angular contact ball bearing, and on the high-speed side, and on the low-speed side, a cross-roller bearing, and the gear train is a strain wave gear. There are 3 integrated sensors here and a bespoke permanent magnet machine. So our actuator is able to lift a half-ton, 9-foot concert grand piano.
Our fingers are driven by metallic tendons that are both flexible and strong. We have the ability to complete wide aperture power grasps while also being optimized for precision gripping of small, thin, and delicate objects. Some basic stats about our hand is that it has 6 actuators and 11 degrees of freedom. It has an in-hand controller, which drives the fingers and receives sensor feedback.
We're ported directly from autopilot to the bot's situation. It's exactly the same occupancy network that we'll talk into a little bit more details later with the autopilot team that is now running on the bot here in this video. The only thing that changed really is the training data that we had to recollect. We're also trying to find ways to improve those occupancy networks using work made on neural radiance fields to get really great volumetric rendering of the bot's environments. For example, here, some machinery that the bot might have to interact with. So we've been training more neural networks to identify high-frequency features, key points within the bot's camera streams, and track them across frames over time as the bot navigates through its environment. And we're using those points to get a better estimate of the bot's pose and trajectory within its environment as it's walking. And this is a video of the motion control code running in the autopilot simulator showing the evolution of the robot's walk over time. And so as you can see, we started quite slowly in April and started accelerating as we unlock more joints and deploy more advanced techniques like arms balancing over the past few months.
We wanted to manipulate objects while looking as natural as possible and also get there quickly. So what we've done is we've broken this process down into 2 steps. First is generating a library of natural motion references, or we could call them demonstrations. And then we've adapted these motion references online to the current real-world situation. So let's say we have a human demonstration of picking up an object. We can get a motion capture of that demonstration, which is visualized right here as a bunch of keyframes representing the locations of the hands, the elbows, the torso. We can map that to the robot using inverse kinematics. And if we collect a lot of these, now we have a library that we can work with. But a single demonstration is not generalizable to the variation in the real world. For instance, this would only work for a box in a very particular location. So what we've also done is run these reference trajectories through a trajectory optimization program, which solves for where the hand should be, how the robot should balance during when it needs to adapt the motion to the real world. So for instance, if the box is in this location, then our optimizer will create this trajectory instead.
I think the first thing within the next few weeks is to get Optimus at least at par with Bumblebee, the other bot prototype you saw earlier, and probably beyond. We're also going to start focusing on the real use case at one of our factories and make this product a reality and change the entire economy. All of this was done in barely 6 or 8 months. Thank you very much.